Ever stop and think about what's really making your phone, your car, or even your coffee maker so smart? Well, deep inside all these gadgets are the secret heroes of modern electronics, programmable logic. So let's dive into this amazing world and figure out how these tiny powerhouses actually work.
I want you to imagine for a second that you're an engineer, back in the early days of digital electronics. If you needed a circuit for one very specific job, you were kind of up against the wall. You had to design a completely custom chip from the ground up for that single task.
And trust me, this was no small problem. The process was painfully slow, it was astronomically expensive, and, get this, once that chip was made, it was set in stone. That's it. If you needed to make a tiny change, tough luck. You had to start the entire process all over again. It was a huge bottleneck for innovation. You can see why people were thinking there has to be a better way.
And guess what? There was. The solution was a total game changer, and it came in the form of something called Programmable Logic Devices, or PLDs. This was a completely different way of thinking about how to build custom circuits.
Okay, so what is a PLD? At its heart, a PLD is like a blank canvas. It's a generic chip that comes from the factory, packed with a ton of logic gates, but its final job hasn't been decided yet. Engineers can take this blank chip and program it later to do exactly what they need. It's like getting a custom chip, but without that crazy custom price tag or the endless waiting.
So, how in the world do you program a piece of hardware? Well, there are a few ways, but one of the coolest early methods was fuse technology. Just picture the chip's internal wiring as a massive grid of tiny, microscopic fuses. The programming process literally blows specific fuses to break connections, which carves out permanent electrical pathways. You're basically sculpting the exact logic circuit you need right onto the chip.
All right, let's look at our first major type of PLD, the read-only memory, or ROM. Now, you probably know ROM as the place your computer stores permanent data, right? But it's also a really powerful tool for creating logic. Just think of it like a permanent, pre-written digital encyclopedia. The secret to a ROM is its internal structure. It's got two main parts. The first is a fixed AND array, which is basically a decoder. Its job is to take your inputs and generate every single possible combination of them. You can't change this part. But the second part, the OR array, is programmable. This is where you get to decide which of those millions of combinations you actually want to use to create your output.
Here's a perfect example. Let's say we want a circuit that can take any number from 0 to 7 and tell us its square. Easy. First, we just create a simple lookup chart, what engineers call a truth table. It just maps every input to its correct squared output. So, the input for 3 points to the output for 9. Then, we program the ROM's OR array to permanently store this chart. And boom! Now, anytime the circuit sees the input for 3, it instantly looks up and spits out 9. It's become a tiny, specialized, super-fast calculator.
And as the source material puts it, this is incredibly powerful. Because a ROM can store a lookup table for pretty much any set of inputs and outputs, it can be used to create virtually any combinational circuit you can dream up. And that's just a fancy way of saying a circuit whose output depends only on what you're putting into it right now.
Now, ROM is powerful for sure, but it can also be a bit inefficient. And that brings us to our next device, the Programmable Logic Array, or PLA. This thing was designed with one goal in mind: maximum flexibility.
When it comes to the simple PLDs, the PLA is really the king of customization. It's the most adaptable and versatile of the bunch, giving the designer an absolutely incredible amount of control over what's happening inside the chip.
So where does all this flexibility come from? It's all in the structure. Remember how the ROM had a fixed AND array that generated every single combination? Well, the PLA just throws that idea right out the window. In a PLA, both the AND array and the OR array are fully programmable. This means you don't have to waste space generating combinations you don't need. You only create the specific logic you care about, which makes it way more efficient for a lot of designs.
Of course, all that flexibility in the PLA also meant it could be pretty complex to work with. So the industry came up with a third option, a sort of happy medium, if you will, the Programmable Array Logic, or PAL. This device is all about striking a practical balance between features and just being easy to use.
The whole idea behind the PAL is a trade-off. It's a lot easier and often cheaper to make and program than a PLA, but the catch is you have to give up some of that ultimate fine-grained control. And you can see exactly why when you look at its structure. A PAL has a programmable AND array, which is great. Just like the PLA,
You can still create your own custom logic, but its OR array is fixed. The connections on the back end are predetermined, which really simplifies the design, but it also limits the ways you can combine your logic.
When you see them side by side like this, the difference is crystal clear, right? The PLA is total freedom, 2 programmable arrays. The PAL is that compromise. You get a programmable front end, the AND array, but a locked-in back end, the OR array. This one little difference is what defines everything about them.
This table really pulls it all together. You've got the ROM, with its fixed AND and programmable OR, perfect for those lookup tables. Then there's the PLA, programmable everything for maximum flexibility. And finally, the PAL, with its programmable AND and fixed OR, giving you that balanced, practical design. See? Each one is a different tool for a different job.
Okay, so we've waded through some pretty technical details. Let's zoom out. Why does any of this really matter? How do these simple ideas end up shaping the world we live in today?
Well, it all comes down to one simple but incredibly powerful idea: consolidation. Here's the big takeaway. Programmable logic devices let engineers pack a huge amount of custom logic, stuff that used to take up an entire circuit board full of individual chips, into one single tiny affordable integrated circuit. This is what unlocked the door for all the miniaturization and complexity we see in modern electronics. These early PLDs really paved the way for the mind-blowingly powerful devices we have today, like FPGAs, which take this concept to a whole other level.
So let's just quickly lock in the key takeaways from all this. First, PLDs with a brilliant solution to the slow and expensive problem of custom hardware. Second, ROMs work like super-fast permanent lookup tables. Third, PLAs give designers the ultimate control with 2 programmable arrays. And finally, PALs give us that perfect balanced compromise between simplicity and power. And that kind of leaves us with one final thought to chew on. The next time you use any piece of modern technology, just think about it. How many of those devices are powered by chips that started their life as a blank canvas only to be perfectly sculpted into the specific electronic brain that makes your world work? I bet the number is absolutely staggering.